Hi, my name is Elizabeth Ramos, and today we're going to be going over Hess's law, which is in chapter 6 in the thermochemistry chapter. So I'm going to go ahead and read the problem to you to make sure that we're all on the same page. So the problem says, ammonia will burn in the presence of a platinum catalyst to produce nitric oxide, which is this guy right here. What is the heat of reaction at constant pressure? Use the following thermochemical equations, and they give you these with these delta H values. So what we're solving for is the delta H of this equation. The cool thing about Hess's law is that we can manipulate the equations given in order to find the delta H for this one, because the sum of these equations should equal this one at the end. So what I'm saying is that we're going to manipulate these equations to make them look like this original equation, and then we're just going to add the delta H's, and that's going to give me the delta H of the reaction as a whole. So I know that doesn't make much sense in words, so let's just go ahead and start, right? So I'm going to compare these equations to this one, and I'm going to change them accordingly. So over here, I don't see N2 anywhere here. So I know that one's going to have to cancel somehow. How are they going to cancel? You'll see in just a second. O2 is supposed to be on that side, so far, so good. NO is also supposed to be on that side, so I'm going to keep this one around the same. However, I see that there are 2 NOs here and 4 NOs here. That usually means that I have to change it, unless I have it in another location. So over here, I see that there is no NO here or here. So this one is the only equation I can change to make it equal to that one. So here I have 4, here I only have 2, so I have to multiply this whole thing by 2 to make it equal. So that means that the new equation for this one is going to be 2N2 gas plus 2O2 gas yields 4NO gas. And then you also are going to multiply the delta H by 2. So it's going to be 180.6 times 2, which I calculated to be 361.2 kilojoules. The units are going to stay the same. So we dealt with that one. Now let's look at the next equation. Here I have N2. I don't see N2 anywhere on there, so I'm going to have to cancel it somehow. I have H2, which I also don't see in my equation, so that one's going to have to cancel out somewhere as well. And NH3, which I do have. However, here I see it's on the reactant side. Here I see it's on the product side. So in order to change that, we have to multiply that by -1. Multiplying it by -1 flips the equation, making the products into the reactants and the reactants into the products. However, I also see that this is a 4 and that's a 2. So what I'm going to do is I'm going to multiply by -2. The negative is not going to make any of the coefficients negative. It's just going to flip the equation. So now my equation is going to look like 4NH3 gas yields, and it's going to be 2N2 plus 6H2. All right, so that's how that one's going to look like. And then we multiply this by -2 as well. So negative times a negative makes a positive, and that's going to be positive 183.6 kilojoules. All right, so we're almost there. Now I have to look at the last one. Again, I don't see hydrogen anywhere on there, so I know that's going to have to cancel. Oxygen can stay there because it's going to be on the reactant side, and H2O is in its right location as well. However, I'm looking at H2O. Here I only have 2. Over there I have 6. So that means this whole thing needs to be multiplied by 3. If you notice, I haven't really touched the oxygens because 5 is an odd number. And it's also in 2 locations, so I just have to make sure that they're going to add up eventually. And as I'm looking, I can already kind of tell, but I'll show you exactly what I mean by that. So I'm going to go ahead and distribute that 3 everywhere, so that means I have 6H2 gas. Oh, I forgot my phase states over here. Let me fill those in. Plus 3O2 gas yields 6H2O gas. And then the delta H is also going to be multiplied by 3, so that's going to give me negative 1451. 1 kilojoules. All right, now that I have manipulated all of them to kind of look like the parent reaction, I'm going to confirm that these make up the parent reaction by adding them all together. All right, so now if you remember back to your net ionic equations, or how to find your net ionic equation, remember if something was on the left side of the arrow and the right side of the arrow, they would cancel out. Well, this situation is going to be very, very similar. So what I'm going to do is I'm going to look on both sides of each arrow, and if there's things on the right and the left, then they're going to cancel. So the first thing I'm going to look at is N2, because that's not in my reaction and I want it to cancel. So I see that I have 2N2 here on the left, 2N2 here on the right, so they're going to cancel. All right, now I see 2O2, I don't see any oxygen, so that one can stay. 4NO, I don't see it on this side anywhere either. NH3, I don't see it on this side. 6H2, I see it here on the left side of this arrow and on the right side of this arrow. And I believe that's going to be it. So now let's go ahead and bring down everything we didn't cancel, and we're going to add these over here. So now I see I have 4NH3 gas plus 2 plus 3 is 5. And then I don't have anything else left over there. Yields 4NO gas and 6H2O. So now let's confirm to make sure it's the same exact equation as the one that we were given. So 4NH3 plus 5O2 plus 4NO plus 6H2O. So that's awesome. Now we just add those together. And when I add those together, I get negative 906.3 kilojoules. So that is the value that we have over here. So that means that the enthalpy for this reaction is going to equal negative 906.3 kilojoules. So remember, let's just a little extra information over here. If they were asking if this was an endothermic or an exothermic reaction, because delta H is negative, this would be exothermic. Means it's releasing heat. And that's how you use Hess's law to find the enthalpy change of a reaction.